Yeah, hi. Welcome to this short tutorial on FrID. This is an automated identification tool for nonlinear structural dynamics and nonlinear oscillators. And we have introduced it in this paper here, Frequency Response-Based Identification of Nonlinear Oscillators, published in Journal of Sound and Vibration 2025. Authored by myself and Professor Balachandran from the University of Maryland in College Park. Before I jump into the topic, I'd just like to point out for the deeper theory, you are welcome to read the paper. Also, there's a more broader research talk on my YouTube channel, which you might want to check out first. In this tutorial, I'm just going to show you how to run the MATLAB code for the experiments in the paper. And from that on, you can build to run your own experiments. That's the purpose of this tutorial. So let's get started. Um, so you can find the code on GitHub or on Zenodo. So GitHub has only the MATLAB code. Zenodo, we also have the measurements, the data, the collected measurements, because they're quite large. So you can just open the link. I'll provide you the link as well along with this video. So here, just press the link, then you are directed to the correct Zenodo page where you can download all the code. So FrID, frequency response-based identification. So here you can just click and download all, and then the download should start. You just select somewhere to save it, and then you're good to go. I already download the script because it is with the measurement data, it's quite large. I think overall we have about 600 megabytes. So I already downloaded the script here on the desktop. So this is the script here. Just extract it to folder. So here, this is now the folder. In there, we find two other folders, which we also unzip. So this is the clamped oscillator. It's the magnetic mechanical oscillator. Extract both of those. So while we extract, just let's go to the paper. So this is the paper here. So now if you look at the first into the results, so the first folder here, magnetic mechanical oscillator, corresponds to this section. So in the results, so this will be the section 3.1. So all the measurements and results from section 3.1 are in there. And then the second folder called clamped oscillator is corresponding to the clamping nonlinear, so section 3.2 of the paper. In the following, I'm just going to run the single degree of freedom case. So I'm only going to look into section 3.11. So where we do obtain measurements, so we work with this setting here with a single beam mounted, and those kind of response curves here shown on the left and on this figure 5. All right, let's get started. So this would be the magnetic mechanical oscillator, and SDOF, a single degree of freedom. So again, here you have three beams. So that will be then the sections of the multiple degree of freedom systems where we work with a 2 degree of freedom system and the 3 degree of freedom system. So that goes going to be in the three and two beams system, and especially so this is here the three beam system. We have certain folders, and then you have the two beam system. You have the case where we have a separated mode, and we also investigate in an internal resonance. So this is section 3.1.3, where we have two beams which are internally resonant mounted. So this is the script. These are the corresponding scripts here. So in the following, I'm just going to go to the single degree of freedom system, and I just start the script. The main script is called beam ID. So I'll just gonna start the script, open the script at MATLAB. I'm using MATLAB 2021A, so that's the main version I've tested it. It should work. It should work with any MATLAB, more or less. I mean, certain MATLAB versions just changed their things, but let's hope you're good. If not, shoot me an email. We can try to work things out. All right. So this is the script here. So I'm going to work now slowly. I'm going to work slowly to the script now with you. So the first part, we're going to load data. So from the measurements are stored in so-called LBM. So these are format that LabVIEW we can write and LabVIEW into LBM files. The measurements are exported from LabVIEW into LBM file, and then I just have a script which imports them into MATLAB. I'll do a little bit of signal processing. I'm not going too much in detail through the scripts here because it's going to be most likely different for your measurements. So that's why I'm not going to spend too much detail there. Yeah. And so now just going to show you the measurement. So the first one just plots the measurement. So there we go. So there we see this is the frequency response curve. So your measurements might look very similar. So we have now here the sweep up, reaching a high amplitude state all the way to maybe 40.8 or something. The highest response point, 40.8, and then we drop down in the sweep up, and then we sweep down, we see lower response pattern. So clearly, like region of bistability, which is a prime signal of nonlinear resonance, and we're going to fit now a model for that. So all right, let's just run the next script. I'm going to now show you a little bit my workspace in MATLAB because it's also interesting for you to see. So what FrID needs is essentially a time vector for each measurement and a response measurement for each measurement. So it is all time series data. So, and this should be provided in cells. So this is here, for example, now so TPO. So this is my time vector for each measurement. So they happen to be the same length. That's not necessarily the case. Depends on your measurement. And now here I have about 122 measurement points so far collected, and the corresponding measurements are stored in this. I've called the vector or the cell array at XPO. So this is the measurements I'm using for identification. So important is that the number of measurements in XPO 122 is the same as the numbers of measurements in the time cell area of time. So the individual lengths here. So the first entry is 2000 is what is how many numbers? 200,001 long, and the length of the first signal also has the same length. This is important. So they could differ. So number 9 could had a different length, let's say maybe for some reason it would be 300,000, then the corresponding time vector should be also 300,000. So for multi-degree of freedom systems, so for example, we have single degree of freedom system, so we have a single column. For multi-degree of freedom system, we have multiple columns down here. This is the main, and the other vector we need is the frequency vector, which is just a single row, essentially. So all the frequencies, so the 122 points are all the points inside this thing here, inside the measured points. Okay, let's advance with the script. I'm going to prepare the data a little bit more. You might skip that, depends on your preference, on your measurement a little. I'm just going to show you and explain how I prepare the data, because I believe that you might see very similar things. So for example, one thing I do here, I divide the periodic orbits, I norm them such that the maximum response here, so this point, which is now 7.1 to the -5, this is equal to 1. And here see here divided by this factor, and so this is now to 1. So I scale all the amplitudes a little bit. I think this helps you with the fitting later on. Okay. Let's advance to the next step. So the next step, I'm just going to explain you here. I delete measurements which are exactly the same, essentially. So now this is the raw data I have on the right-hand side, and you see that for certain frequencies, for example, for here 38.6, we see two measurements. They have the same frequencies and almost the same amplitude. This is because here we are not in the region of biastability. Here we only have a single steady state. And I don't want to use this point, which is essentially the same twice during fitting. I only want to use it once. So I run some script to detect whether the frequency here now 38.6 is measured twice. And if this is selected, seen twice, and the amplitudes are almost the same, I'm going to delete one of the points. So this gets rid of all the repetitions, and then we have a unique points for every frequency we don't have the same amplitude twice, essentially, in here. Now the next point is here. I'm just going to show you, run that. So is the phase. So I'll always check the phase of the supply periodic orbit. It turns out the way I obtain measurement, the phase in the individual time series is not aligned because the reference is not added yet. So that's why I now adjust all the phases according to the reference signal, which I have control periodic orbits. And that's what the script does. So here I essentially shift now the time a little bit such that the phase gives me such that they are all aligned with the same phase with respect to the control signal. And this gives me here this phase, this phase of the response with respect to the control signal, and then we see resonance. So here this is we see a shift of the response the response phase by pi, and we see here that we have, this is the region of biastability, two different phases, and technically the unstable branch would connect those two here. I'm going to show you now how it would like without adjusting for the phase. This would be now if I don't take the normalized time. So here that's where normalized time, I just take this time vector and I'm just gonna plot also these amplitudes here, which are essentially the same, only the non-normalized time. So let's just plot this here. Oops. One second. Yeah, so this is the blue points are what we have before. So this is nicely aligned phase, and red, the phase is all over the place. Um, so we had to correct that, and our correction gives indeed nice results. So this might be the case. Check your phase before you apply it. If the phase is reasonable, might not be as exactly as this curve. So where we have a phase jump by exactly by 180 degrees, which is you should observe in resonance, but depending on your measurements, it might look a little different. But just check if that's what you kind of expect. All right, I'm just going to delete the lines I've added here. So the next, I'm going to estimate the noise level here, and this runs pretty quick. So this is now, I'm just going to go to the paper. So this is now here in the methods, in the identification. So the first step where we estimate the noise level. I think I have somewhere is the, yeah, exactly. So here we kind of now estimate this red line here. This is the noise flow, and all the amplitudes below this noise flow are terminated in the following. So the formula for terminating the noise flow is formula 16 here, and the implementation you can find here. Noise estimators, this is the periodic orbits, this is the time, this is the frequency. So 500 now is the maximum frequency I allow for. So in this formula, you need to supply, you need to supply some kind of some frequency, and I take 500 hertz to be the maximum. No, this is the second entry, so 500 rats is the maximum, and 500 is just the number of samples I do. So I think in the text it says we do the yeah, so we kind of need to estimate an average. So we kind of want to take here, we calculate a lot of different amplitudes for a lot of different frequencies and then take the average. And 500 is now the number of points I select in this average. And 500 is the frequencies I use to calculate the amplitudes of the response. This is, yeah. So here. So now we are coming to a little closer to the actual identification. So here now we select, now we are building, let's go to the paper. Here now we're building this big matrices, matrices A and B. It's in actually A and B here in line 15. Equation 15. And so what I do is, so what we do here is, so we do, we transform the response in the frequency domain. So we need a number of considered Fourier modes, which is in the paper's capital K. So that's what we need to select. So this is an important one. So now this is called the parameter n Fourier modes, which is 2 in this case. I've selected it. And the other one is the degree of polynomials. So just as a reminder, this is the model here, so of which is fitted by FrID automatically. And so these are now the library functions, and the script uses a polynomial expansion of the library functions, and you can select the degree of this polynomial. And this degree of the polynomial is just polyorder here, the function polyorder. And the last number you can select here is the number of Fourier modes in the forcing. So the forcing is also expanded. So this is the right-hand side, the forcing. It's also expanded in a Fourier series, and capital K is now the number of Fourier modes. It usually makes sense to select the full number of modes in the forcing to be the same as the number of Fourier modes. Definitely not higher, because they would be truncated anyways. But you might select the number which is less. Doesn't it is depends on your application. So now this script here builds the big matrices. I'm just gonna go back to the paper here. This would be in this line. So we're going to build this matrices in equation 15. F. And so we need for that, we need the responses. So the as I've shown you now, this is a bit renamed, but this is essentially so this is now essentially a cell array. This is a cell array of responses. T is a cell array of time series of times, so the time for each response measurement. This is the number of Fourier modes. This is the frequency for each measurement. This is the dimension polynomial. So this is the polynomial order we need to supply. This is the number of Fourier modes, and then the noise level. And then if I now run this script, we build the matrices. This gives you a little bit an idea of the progress. Right, and then you can see that this builds the matrix takes a little time. We do a lot of this is where works a lot of Fourier transformation in this script. But I'm just going to open it real quick after this has completed. So it gives you, says also matrix build. I'm just opening it. Right. So you can technically parallelize that. So you can just write off 4, you can just write part 4, and then you would use parallel computing. So you would be much, much quicker, which is handy if you work with either more number of polynomials. So if you increase many, many polynomials, or have more dimensions, so your measurements is multiple dimensional. So I've done it, for example, for the 3 degree of freedom system in the paper. But of course, yeah, MATLAB always takes a little bit of time to start the power parallel computing tool and so on. So I've not selected it here because it was not unreasonably long. But you can just add parallel. You can do this in parallel, and this will go much quicker depending on how many cores you have. All right, let's go back to here. So we were here, and now we have built the matrix, and now this is the essential step for frequency identification. So if you have prepared your data correctly, you can actually already you can all skip all the lines all the way up to line 140 essentially. So that's actually where we start. And here, that's why we do the actual system identification. So here we set the tolerance. Right. So now there are important parameters to set, which is the tolerance parameter. Yeah, and the rest is not so much important here. So and then we run. So this is the automated script. So the automated script takes in the matrices A, B, and then the noise level for truncation, and then the tolerance vector. So the tolerance vectors I'm going to show you later. And this is just something I for displaying. I'm just going to run the script here, and then you can see, let's just take this out. It runs pretty quickly. So it starts, so it first checks that the the residual error. So the best fit we can get is 0.006, 0.007 essentially. And this is less than the tolerance we've selected. We've selected 0.008, which is larger. So we can specify the equations of motion. Um, then, oh no, actually I'm wrong. So what it first does, it detects redundant data. So that's the step. Let's go to the paper. So identification. So noise, we've already taken care of the noise. And now the truncation goes to this part here, where we delete almost linearly dependent vectors. So if two columns of the big matrix A show in almost the same directions, that's not ideal for identification. We just delete one of them, and that's what happened in. Just gonna delete that. So what, and that's what exactly what happened. And so this is the polynomials, the corresponding polynomials that get deleted. And then it checks the residual error, which is less than the supplied tolerance, and then it starts specifying. And now it successively includes this now the candidate functions. So this is now described here in the simplification routine, where we the forward stepwise selection procedure. So if we select polynomials which reduce the fitting residual the most, and then successively include them until we have reached the predefined tolerance. And the predefined tolerance is the tolerance you set here, which is 0.008 in my case. And so we can see here now that so the first polynomial we have identified is x1 in our case. So we only have one coordinate. So this is the stiffness. Then the next one is the quadratic. So it's scales with x cubed, x squared. So this is a quadratic stiffness term. The next one is going to be the cubic stiffness term. And we can also see the relative error. So the first one reduces, is already 94% of the whole fitting residual. So including the stiffness does by far the biggest, the linear stiffness. And then we successively decrease this fitting residual. So now we have a fitting residual of about 0.02 after including the cubic stiffness. Then we see that the forcing amplitudes, the external forcing is included, and then some damping comes up. And after the damping, we have reached our predefined tolerance, and we come up with a model here. And the model is, we can also display it. So the next section essentially just displays the result again. So this is the equation. This is the coefficient. So this is the linear stiffness. This is the linear damping, quadratic stiffness, cubic stiffness, forcing amplitudes, and these are the non-select. These are all the coefficients. They are selected to zero. So here the coefficient selected to zero. For example, the second harmonic of the forcing is set to zero. Like the odd, so these terms are set to zero, also nonlinear damping is set to zero, and so on. So for example, this would be now the linear stiffness, and so this would be the omega zero squared. So this would be omega zero divided by, so 38.39, 38 roughly is the linear stiffness of the thing. Do we have the plot open? So yeah, it's somewhere, it is suspected to be somewhere around here. That's a value that could make sense, definitely. So just take this out. So this is, so you can check roughly if your identified values make sense. So now we can vary a lot of parameters in FRID. And so one of them would be, for example, vary the parameters, the number of polynomials included. So we can also try number polynomial 5. Then we also need to rebuild the matrix. This also just goes completely analogously. Just takes a little longer. So now we see that by number 5, we have a larger number of polynomials for the right-hand side. So the building the matrix takes a bit longer. Just remind yourself, we can also use, we can parallelize the whole thing. But it will eventually get somewhere. And after this is done, I can just run the identification procedure again. Let's see. And then we pretty much end up with pretty much the same model. We see that the coefficients are essentially the same, identified coefficients. Let's just the result might look the numbers, individual numbers like might differ a little bit, but I doubt it. And the reason is probably that most of the higher order polynomials are excluded because they're probably just below the noise floor. So for this measurements, going to higher polynomials does not really make sense. Of course, we can also try to have more Fourier modes. Let's say we just do 3. Again, we need to build the matrix now. And so now we just do the expansion. I'm just going to go here to the script frequency domain. So we do all the expansions here. The capital K now is 3 in our case. Previously was 2, and now it's 3. So might be a little more data there. So now we see that the relative error is 0.009, which is larger than the specified tolerance. So we cannot sparsify the system. So we cannot reach the tolerance we want to have. We could technically display the result. So this is this is a non-sparse system, a lot of coefficients, which is questionable, but we can also just increase the tolerance. So we can set, for example, the tolerance to be 0.1, set the tolerance to be 0.1. And then we see that now, because our tolerance is 1%, which is larger than 0.009, and then we include coefficients again. Now we see that we include the linear stiffness and again, cubic and quadratic stiffness. There's a new term coming in, which was there prior not. So this is x times the velocity squared. So this would be a conservative term. This is now that nonlinear damping. This is the velocity squared times this position squared times the velocity, and also higher order forcing. And here's some linear damping. So that will be the result, which are still within reasonable. So all these coefficients are explainable, at least to some extent are explainable. And but we can also think about, for example, setting the tolerance to higher value, so we get rid of some coefficients if this is needed. The last, yeah. So let's go back to that. So I've shown you how to vary the polynomial order, the number of Fourier modes, the number of the expansion of the external forcing can also be varied. So one parameter I've shown you to set as important is the tolerance here. Let's just build that, and I think we had. So let's just run the solver tolerance 0.1, for example. And if we do only 0.1, We get an, I'm just going to display the result. So this is the result now, which would be an undamped system. So this would be this has only stiffness terms and forcing terms, so no damping. So if we uh, in reality, in nonlinear structure dynamics, we suspect some damping, so we could already see that this model will be not performing too well. It will be still not bad, I think, for certain applications. So in this case, this already tells us maybe we should increase the tolerance a little more. We increase the tolerance to, let's say, 0.9. Let's do that real quick. So I think that's probably why I had it to 9.8. Yeah, and then we can see now that the forcing the nonlinear damping is included in the fitting. Let's just continue here. This is the model we started with. So one other parameter you might want to look into is, I'm just going to open FrID here. So this is essentially the core function that does the fitting. So here in line 457 to 469, this is here compared to the paper is where we remove the linear dependencies. And I'm going to go, so this is essentially this algorithm one here. And there we kind of need, so this is now here, this is where we compare the lengths of two projection of the vector and the vector itself. And if this is lower than a certain threshold, then the thing gets included, and if not, then it's not included. And this threshold is set here 9.0995. Depending on your application, you might want to change that. For this type of measurement, 0.9, 0.95 is good. If your measurement is very noisy and essentially you can only trust the first harmonic, then you might want to set this to a much higher tolerance, or even set this, skip this step. That's what I have observed. But ideally, you have very clean measurements where you can trust the first harmonic and so on. Then you just then it displays the deleted data, and then we do the fitting here. So this is the forward stepwise selection, where we repeatedly include a new identified polynomial, and then check if the tolerance is met or not, and if not, then we just look for the next polynomial included, and so on, and that's the whole identification procedure. Okay, go back to the script where we at. Yes, so one thing I just told you, like how many harmonics you can trust. For example, here I can show you a little bit the measurements I have. They're all the same. I'll just put them in a different. So we can see here, so this is the first harmonic, this is the second harmonic, and this is the third harmonic for my measurement. And we can always already see that that the second harmonic is a little more noisy. So this is a very clean, you can see that there's a very clear lines here in the first harmonic. In the second harmonic, it already gets distorted a little bit, but it's still okay. Similarly, the third harmonic, we see some variations, but it's still nice, more or less nice and clean. You might want to check those kind of projections in your system. I've seen measurements where after the first harmonic, this gets very, very noisy, and then I would urge you probably want to truncate at the first harmonic everything. Okay, but nevertheless, so I can show you one run where we truncate everything at the first harmonic. So let's truncate everything at the first harmonic. Now the building the matrix is a bit quicker because we only have one harmonic, one projection in the whole thing. Let's see. So we see that it includes stiffness and forcing terms. So we would need to decrease the tolerance again further to get some form of damping. What is the yeah, so then we would need to decrease the tolerance quite a bit to get some damping. So have um, a structure model which includes damping. So we can see that this already automatically, for example, if you work with one harmonic, it excludes the second harmonic automatic the quadratic stiffness terms automatically. This is expected because quadratic stiffness terms in the first expansion don't produce first harmonics, so this is perfectly reasonable. So if you work with only with the first harmonic, you can only get perfectly symmetric models, so no asymmetry in the data. It's something to watch out. There's nothing wrong with that. Is something I would like to point out. All right, let's go back to two harmonics and yep, run the script, set the tolerance again. I think 5 here, and then I'm just gonna go a little bit through the plotting really quick with you guys, but then I think that we're almost at the end of this tutorial. Yep. All right. Start identification. This displays the results. That's the result we had earlier. And then the script here gives me a way to, this is an automated sweep now, so this computes the sweep from the data. So now we see this is the progress. It's going to take a while now because we do like now simulations of the sweep to compare them in the end to your measurement. Um, so it creates a frequency vector, which is the same as supplied measurements. Might be want to change that. It takes the parameters, the forcing, and then just some initial conditions and some time vectors. Essentially, that's what's given in the function. You can look at that. Yeah, you can also program your own depending on your application. It's just a validation step. Simulation takes a little bit of time, can be probably made quicker, but I'm not going to go too much into the detail there. I'm just going to show you hopefully a nice result and then walk you through the rest of the script, but probably not running it because it will take some too much of your time. All right, we're almost halfway done with the simulation. Is there anything else I can tell you about this? I should pull me up the paper here. Did I forget something? No, I think I mentioned all important points. Yeah, so as I said, this tutorial only shows you how to run the script. For more theory, I recommend reading the paper, or also for an overview, watch the other my research talk on this channel as well. Um, But I think by now you have a fairly good idea where the important knobs are to tune in this identification routine. So just to memorize, to reiterate, so what is important to supply. So essentially, the everything up to this point 100 line 140 is just preparation. So pre-processing. The real identification goes from line 140 to maybe line 170 here. So that's still so. And the important parameters we need as an input is time series of the measurements. So cell vector of measurements, a cell vector of time instances. Frequencies is important. And that's essentially it. So the rest is just parameters we've set in I've explained you a little bit how to set them. Exactly. So I think here so these are the two vectors. I'm just going to iterate them here. So this is the vector I'm using, which is Z. So this is the cell vector I'm using for identification. Just going to open it up, close the other ones. So this is now, so 98 measurements are used for fitting in the end. And each measurement is in here. This is a number of time steps times the dimension is the dimensionality of each entry. And the corresponding time vector is this guy, which is there. So this is also 98, so 98 measurements, and this is the number of time steps here corresponds to the first dimension here. That's important. So in the meantime, I think we have succeeded calculating the frequency sweep, so simulating frequency sweep, which we see here. Now I'm just going to load the amplitudes from the measurements. Script, and this plots now force response curves. So this is now two different force response curves, or yeah. So this is the force response curve for the first harmonic. So this is the amplitude now. This is the first harmonic, where we see a very good fit, and I think you can see this plot also in the paper. Here you see the fit for the other harmonic. So this is now if you project the response and the measurements in the first harmonic and the third harmonic, we see that the fit here is not that good. So it appears to be not that well. So we see some deviations for the second and third harmonic. So you might, if you are really interested to fit the third harmonic very, very well, you might want to increase your model, make it more complicated, and then I'm sure you can fit that better. But also be mindful that here the scale, this is 10 to the negative 3, and this is 10 to the negative 2 compared to 0.1 or 0.5 here. So although it appears as not a very good fit, if we put it in the same scale here, you would see no difference. So this fit actually just appears worse than it actually is. Okay, so then I think that what we do on in the paper later on, I'm just going to show you the plot because I'm not going to run the. So yeah, so what we do then, so the nice thing is now after we have settled to a model here, so this is the single degree of freedom system I'm looking into. So after we set the model here, we've fixed this model, and now we can, of course, vary the right-hand side, the forcing. And we can, for example, simulate the force response to different type of forcing amplitudes. So, and this is what we have done here. This is what we have done here. So that we do the simulations and then afterwards also the measurements for different excitation levels. And this is here the script that does this. So just reloads the measurements. And I'm just going to show you now how to change. So what we do now to get the sweeps for other forcing amplitudes is essentially now this thing here, this entry needs the forcing amplitudes. And since this forcing amplitude I've used for identification is at the level 1.5, I just multiply the forcing the right-hand side with the new level divided by 1.5. So now if instead I want to have the forcing for 2, for the force excitation level 2, for example, I divide the forcing by 0.15 and then just times 2. And you can just essentially now scale the amplitudes here in the simulated sweep, and then you get different type of sweeps. Similarly, you can compute conservative the conservative system. You can compute nonlinear normal modes from this setting. For that, you need to nonlinear normal modes are defined for the conservative unforced limit. So you would need to set C to 0 and forcing to 0, and then you can compute the families of periodic orbit, which then are backbone curves, which are conservative normal modes, which are also themed as backbone curves. And yeah, this is done in the script later on. I'm not going to go through that. We have used Coco. You can look in the parameter if you want, but I'm not going to run. So yeah, this is an advanced topic. All right. So just to iterate it again, the important lines for using FRID are somewhere between line 140 and 160, 170. So this is the important things you want to look into. So I hope it now became a little clearer how to run the code. If you have any questions, feel free to reach out, and yeah, have fun running this on your measurements. I'm excited to see your results.